welcome back. So, today we will be again looking back into our Karatsuba multiplier. So, I will continue with what we were discussing in the last class, and we will be rather trying to cover these topics on how to implement an end-to-end Karatsuba multiplier. We will be also discussing another important operation which is called as a modulo operation, as we have seen in the last class that when we are doing multiplications, then we are splitting, right? I mean, then we are spilling over the field. So, we need to again do a modulo operation so that the result gets back into the field. Okay. So, there are very efficient ways of doing that, in particular when you are talking about GF2 arithmetic. Okay. So, this is a reminder of what we where we stopped in the last class. So, we want to implement a 233-bit multiplication or 233-bit hybrid Karatsuba multiplier. So, the strategy is that I take 233 and I start decomposing them like 116 and 117. So, I take two parts, and then I again take 116, I can again decompose into say blocks of equal size of 58 and 58. 117 I will again decompose at 58 and 59, and then I will do that gradually until I have got dimensions which are lesser than my threshold. The moment my dimension becomes lesser than the threshold, I switch my strategy. I apply either the general Karatsuba, or if I may even apply my school book algorithm. But the main point is that I need to switch at a proper choice of the threshold. So, one should vary the threshold and see for what kind of proper thresholding, right, for your platform you get an efficient performance. So, if I want to implement, so I will take an example from Verilog program, Verilog hardware description language or HDL, and we will discuss about how to implement a Karatsuba multiplier in hardware. So, therefore, it's a combinatorial block. So, I have got two inputs of dimensions 233 bits, because A and B are both GF2 power of 33 elements. The final result is D, which is again in the field. So, therefore, the result is also in 233 bits. Okay. Now, when I am doing a normal multiplication with A and B, I know that my result can go up to 465 bits, okay, because when I am multiplying two numbers, then essentially there can be an increase in the field size. So, therefore, in this case, right, when you are taking GF2 power of 233, the degree is maximum 232. So, likewise for both for A and B. So, if I take AX and BX and if I multiply them, then my degree can go up to 232 into 2, which is 464. So, therefore, right, what I need to do is I need to do a modular operation or a modulo operation with my with a specific primitive polynomial. So, the result essentially gets back into the field, and I finally get D, which is again belonging to GF2 power of 233. Okay. So, how do I realize all these blocks? So, as I said that when you are taking a Karatsuba multiplier and you would like to implement a Karatsuba multiplier, so this multiplier operates on 233-bit inputs and gives you a 465-bit output, and the multiplier uses sub multipliers with the operands as we have described in this figure. The initial multiplier is of course a simple Karatsuba based, but however a threshold of there has to be a specific threshold after which we are switching, right. This is the overall strategy. So, when you are so basically like let us just first concentrate on the simple Karatsuba decomposition. When we have taken two arguments of dimensions 233 bits, how do we decompose them into dimensions of 116 and 117 and do the Karatsuba operation? So, there are some something that, so this is the overall structure of the operation. So, this is the code for doing the Karatsuba operation. As you see that I just take two elements like 233 bits each, and I want to apply the Karatsuba operation. So, when I am doing a Karatsuba, as I said, right, then I have got three multiplications that I am doing. Okay. So, therefore, the three multiplications are denoted as KSM1, KSM2, and also there is a KSM3. So, these are the three instances of doing the Karatsuba operation. So, as you see that the first thing that I have done is that I have split up A into two parts. So, one which has got from 0 to 116, which is one part, and the other one which is like from 117 to 32, which is the second part. Likewise, B is also split from 0 to 116, which is one part, and B 117 to 32, which is the other part. Okay. So, we often say that this part is the lower part and this part is the higher part of A. Likewise, this is the lower part of B and this is the higher part of B. So, when I am multiplying these two, I am getting the result in M2. When I am multiplying these two, I am getting the result in M1. So, when I want to do the other Karatsuba multiplication, then I have to take like the higher part and the lower part of A, and I have to do an XOR. So, therefore, I do an XOR of the lower part of A with the higher part of A. Likewise, I do an XOR of the lower part of B and the higher part of B, and then I essentially take the lower parts and the higher parts, and then finally I do a Karatsuba essentially like between the AHL and the BHL part. So you can observe here that I am essentially doing a multiplication between AH plus AL and BH plus BL. So therefore like I am basically trying to multiply H plus AL, which is the higher part plus the lower part of A, and BH plus BL, which is the higher part plus lower part of B, and I am getting the result finally stored in M3. So now when we have done that, so when we have basically like got the result, then I should get the result which is a D, but D is now a 465 bit value. So therefore I of course need to do a final modulo operation. So now let us see how we can do this operation. That means how we can actually do this 233, do basically do the Karat-Suba operation. So let us just focus on how we can combine the different components. Okay. So for this, right, I mean we can actually again resort to we can actually see how the operation is done, and let us try to see how we can do this operation. So let me first just take so this is your AH plus BL. So let us write just AH x plus AL. So this is nothing but AX. Okay, so AX is my polynomial which has got two parts, AH and AL. Likewise, right, I have got BHX, which I have written as BX, which is written as BHX plus BL. So this is my high part and this is my low part. And when I want to do AX into BX, that means I want to multiply AX with BX, then essentially, right, I mean we can observe that I need to multiply HX plus AL with BHX plus BL. Okay. So let us take an example. So in our case, AX is nothing but A232 x power of 232 plus so on till A0. So all these coefficients are 0, 1 elements. Likewise, I take BX, which is B232 x232 plus so on till A0. So AX is therefore equal to, if I take A0 plus so on till A116 x power of 116, this is the lower part of A, plus x power of 117 multiplied by A117 plus so on till A232 x 115. Okay. So essentially, right, I mean when we are doing an operation between AX and BX, so likewise, right, you can actually take BX and also write in this form, which is B0 till plus B116 x 116 plus x power of 117 B117 plus so on till B232 x power of 115. So therefore, right, what you can actually do is, in a compact manner, you can write this AX as AX equal to AL plus x power of 117 AH, and likewise you can write BX as BL plus x power of 117 BH. Okay. So let me correct this and write that this would be something like so this is just to like don't take it as a multiplication with x, but this is just to indicate that I am combining the higher part with the lower part, but the combination is done in this way. Okay. So therefore, right, when we would like to multiply them, then you can easily observe then how the multiplication works. Okay. So therefore, let me clear this and just try to write the product. Okay. So this is easy. So we can, what we are basically doing is that the product is ALBL plus x1117 ALBH plus HBL plus x power of 234 HBH. Okay. So this is my final result. Okay. So now now we can try to observe this in a figurative way or through a figure. Okay. So here what we see is that this is my lower part. So this lower part is essentially aligned with the right. That means this is aligned with 0 for example. So, this is my ALBL. Okay. So, this starts in this case from 0 and continues till 232 bits. Okay. Likewise, we see that this part, that is ALBH plus HBL. So, this part, that is ALBH plus HBL, which we have represented as AL plus H into BH plus BL plus ALBL plus HBH. So, these are decomposed into 3 parts. So, this actually starts from 117. So, therefore, if I draw this line, there is a line at 117 from which these 3 parts are essentially starting. Okay. So, essentially what I have got is 3 parts, and the 3 parts essentially are nothing but ALBL, okay, likewise HBH, H plus AL and multiplied with BH plus BL. So, this is my third part. Okay. So, this starts from 117 bit position, and essentially, right, if you start, or if you say that this is 0, then this is also 232 because it is 0 to 232. Okay. And now, one can observe that there is another part which essentially starts from 234. Okay. So, that means if I leave out some bits for that. So, essentially I start from here and I get this part which is nothing but HBH. So, HBH again starts from 234 bit position, and that you can observe here, that is, it is x to the power of 234. So, it starts here and essentially continues and comes here or comes over here. So, now what we have to do is we have to combine these terms. We have to combine these terms to get the final product. So, one thing which you can easily observe is that from 0 to 116, that means essentially before 117, this is just nothing but the copying of the ALBL. So, therefore, this part is very straightforward, right. I mean, you just need to copy from 0 to 116, and that is nothing but copying ALBL, which is nothing but essentially your like you have just copied the lower part actually. However, if you just observe the 117 bit, essentially the 117 bit will have or rather from 117 to 232, you see it is the addition of 3 components. These 3 components are being added up. Okay. So, that continues from 117. So, this continues from 117 bit position to 232. So, we are basically adding up this M1, M2 and M3, 3 parts. Okay. The 233 bit, right, is something which is interesting because it comes in between. You are still adding up. You are essentially so in this case when you are doing this addition, you have got 4 parts. This part, this and this and this. So, you have got 4 parts which you are adding, but for only 1 bit position, that means the 233rd bit position, you are only adding this, this and this. So, there are 3 bits which you are adding. Okay. So, that gives you the 233rd bit. Okay. On the other hand, right, for the remaining parts, that is 234 till again the end of this, you again have for certain position you have got, or certain bit positions you have got 3 parts which you need to add, and for the remaining parts you just need to only add you just need to copy the HBH values. Okay. So, this is a summary of how the overall computation looks like. Understand the correspondence here. So, here you can observe that, as I said, that the remaining parts are, I mean the lower parts are just copying of one of the lower part which is M2, we have just copied it. From this part to this part, you have, that is from 117 to 32, you have got 4 registers which you are XORing. Okay. For the 233rd position, you have just 3 bits to XOR. Again, when you are going for the 234 to 347, now this 347 you can easily calculate by the relative position. And these are, here you have got again 1, 2 and 3 and 4 values to XOR, and then finally you have got the remaining 348, 349, which is an XOR of 3 bit positions or 3 registers, and finally you have got the higher part which you are just copying. Okay. So, this gives you a mechanism of how you can combine the partial results and you can get the corresponding Karatsuba output. Okay. So, now we can actually go into, we can describe the general Karatsuba. So, general Karatsuba, as I said, is where you decompose, instead of decomposing into 2 as we have seen in simple Karatsuba, you decompose it further. Okay. For example, if I take AX, suppose I decompose AX into A2, A1 and A0, that is 3 parts. Likewise, I take BX and decompose into 3 parts. then I can denote D0 as A0 B0, D1 as A1 B1 and D2 as A2 B2. I can still write the final result Ax and Bx in terms of these coefficients. Okay, so you see that here I also define D01 as the Karatsuba of A0 A1 and B0 B1, just like as we did in the simple Karatsuba. Okay, so this is easy to check that this is your corresponding output result. The interesting part is that when you have decompositions of this form, then you have got each of these terms which have got 3 arguments or 4 arguments. Okay, so now if you observe or remember the old discussions that we had on the lookup table structure for the FPGA, it already has got fixed inputs. That means if you are not using those 4 inputs, for example in a 4 input lookup table, then you are basically underutilization of the lookup table. Okay, and that is why general Karatsuba seems to be better utilizing the lookup tables, because it always have got these number of input arguments for each of these terms. Okay, so therefore you get a better utilization in the general Karatsuba, but as I say that when you are doing implementing a general Karatsuba, then it seems that the gate count increases. So therefore for higher dimensions it is not a good choice, but for lower dimensions it is a good choice. So therefore what we can do is we can actually in the higher dimensions implement a normal simple Karatsuba, but when we switch back or when we go down to the lower field sizes, then we can switch to the general Karatsuba. So therefore what we do is you can actually do this, and when you are going for the smaller degrees like 14 and 15, you can actually switch to the general Karatsuba. So here is a link which you can follow where you can get a complete synthesizable Verilog code for this design, which you can where you can do further experimentations. There is another important structure which we also need to implement, and that is called as a modulo arithmetic, because you see that as we have said or discussed already, right, that our field sizes have increased, and therefore right we need to do a final reduction operation where we bring back the result into the original field. Okay, so here is a very simple way of how we can do that. So I will again take the example of my Karatsuba operation. So I have got the final result from 0 to 464, and I want to bring the result back from 0 to 232. Okay. So therefore, right, I have to look into my irreducible polynomial. So in this case, the irreducible polynomial is x to the power of 233 plus x to the power of 74 plus 1. Note that 74 is in general lesser than n by 2. Okay. So now what we do is that if I want to do this reduction, then a very common way of doing that is we replace x to the power of 233 by x to the power of 74 plus 1. So that means, right, if I represent this x as alpha, then alpha to the power of m becomes alpha to the power of n plus 1. Okay. So therefore, right, if you have got any element which is more than 232, that means it is 233 for example, I can replace it by 1 plus alpha to the power of n. Okay. And likewise for all the elements which are more than that. So therefore, right, what I can do is that I will reduce it, and if I reduce it, right, then I will see that so these are my corresponding reduced elements. So these are all elements which are or positions which are outside my field, and therefore it goes from alpha to the power of m to alpha to the power of 2m minus 2. Okay, so you can plug in, for example, m equal to 233, and you note that 2 into 233 minus 2 is 464. That means the maximum position here, maximum value here. So all of them are being reduced by the field, and you can see are reduced by the irreducible polynomial. And you can observe that these terms like 1 alpha till alpha to the power of m minus 2 are now all inside the field. Okay. For example, m is 233, so therefore m minus 2 will stand to 231. Okay. So therefore, right, you see that it becomes, so you can see that there is a small gap here in this diagram to indicate that it is 231. So therefore, right, this is the corresponding part which is being shown by this white rectangle. Okay. So I have reduced it, and therefore this is my corresponding reduced result. On the other hand, there is another component which is alpha to the power of n till alpha to the power of m plus n minus 2, which if you consider, right, here it starts from alpha to the power of n. So n is 74. So it starts here at 74 and continues beyond. So till a point, right, that is it reaches 232, it is fine because it is inside the field, but beyond that again it exceeds the field. So you have to again reduce it. Okay. So how do you reduce it? Again you take these elements and do a similar operation, and then you reduce it. So again you basically bring it here, and then this is the part, in this case, right, with just one reduction it gets into the field, and therefore the final result is in the field. Okay. So you can observe that when you are doing this reduction, right, and the finally when you are giving the result, then the computations which you are doing are just employing Boolean XORs. Okay. So therefore the entire reduction operation can be done without any complicated division or finding out the remainder. Okay. You can just do it simply by using Boolean XORs, and therefore the reduction operation or the modulo operation in GF 2 power of n arithmetic is very, very efficient. Okay. You can do it in a very simple manner. Okay. So likewise, right, I mean you can find out more details in this book. Okay, so this is like I mean this is just an overview about how you can implement the two fundamental structures like the Karatsuba multiplier, both the simple and the general Karatsuba, and also right how you can do the modular arithmetic. Okay, so with this, right, you should be able to follow more discussions which are given in the book, which essentially I am omitting for the sake of time. And finally, right, just to conclude, what we discussed in both the previous lecture and this part is that finite field theory is very central to cryptographic algorithms. Understanding finite fields is crucial to develop efficient architectures for cryptographic algorithms. Binary fields offer special advantages in terms of efficient designs. It is more compact, more optimal in terms of its representation. We studied few important finite field operations like in characteristic 2 in specifically, I mean like the Karatsuba multiplication, the squaring operations, and also the modular arithmetic. Okay. So thank you. So we will continue again in the next class with more discussions on finite field architectures and other subsequent topics. Thank you.